Hey everyone. Today we're going to be taking a look at section 4.5, which is all about implicit differentiation. So if we took a look at this equation here, y equals 2 minus 3x squared, um, we could say that y is a function that depends on x. So this is something that we're used to saying is instead of y, we're going to call this f of x. So we could rewrite our equation as a function saying that f of x equals 2 minus 3x squared. So in order to minimize the number of symbols that we need to use, we might get into the habit of writing functions as variables. So instead of calling y f of x, we might think of y more like y of x. So the function name would actually be y. So y, which is a function of x, is equal to 2 minus 3x squared. And this hopefully will make a little more sense in just a little bit. So on our last slide, we were saying that y is both a dependent variable and a function symbol. So for example, we could evaluate at a given point where y does have a fixed value, but we're also using y to represent a function. And we're definitely going to see a couple examples of this moving forward. But the reason why we're doing it is it's a very convenient notation, and it doesn't really take anything away as long as we recognize that y is being used in multiple ways. So other examples that you might see, here we have x as a function of t. So x equals 2t squared minus 3t plus 1. But we're acknowledging that x is a function of t. This is actually really common in like physics, where x is a position and t is time. But again, we can do this with any variable. We can have z be represented as like z of u. So this is a function in terms of u. And we can have r equals r of s, where we're talking about a function in terms of s. So this will be very, very helpful moving forward. We're going to see that in this section with implicit differentiation, and we're going to see it a lot in the next section with related rates. Something else that we might need to take a look at are functions involving more than one variable. So if we took a look at like this, or this function at the bottom, we can have f of x and y. So this is when things depend on more than one variable. We find that happens a lot. If you think about areas, area, like for a rectangle's base times height, we have two variables that determine what our area is. So we can find functions that depend on multiple variables. So consider the following equation. 3x squared plus y minus 2 equals 0. So if we were to solve this equation for y in terms of x, we would get y equals 2 minus 3x squared. And that's a form that we're very familiar with. And they say that both equations define the same function, where x is an independent variable and y is the dependent variable. So we could really write y as f of x. So we could say f of x equals 2 minus 3x squared. And this is all from like algebra 1 kind of stuff. We're used to kind of using y and f of x interchangeably. So if we wanted to take the derivative here, it would be as simple as using the power rule. The derivative of 2 is 0, and the derivative of negative 3x squared is negative 6x. So I could say that f prime of x is negative 6x, or we know that we could rewrite this as dy dx. The derivative of y with respect to x is negative 6x. So this is an example of differentiating explicitly or directly. So let's take a look at an example of implicit differentiation. So implicit differentiation is really talking about taking a derivative indirectly. So we're going to start with the same function, 3x squared plus y minus 2 equals 0. And rather than trying to solve for y, what we're going to do is we're just going to think of y as a function. So we're going to y of x. So we just replace y with y of x, acknowledging that y is the dependent variable and x is the independent variable. And now what we're going to do, without solving either side, we're just going to take the derivative of both sides. So you can see it's d dx of 3x squared plus y of x minus 2 equals d dx of 0. Now we know that when we are taking the derivative of a sum, we can take the derivative of each term individually. So it's almost like we can distribute this derivative. So we're going to take the derivative of 3x squared plus the derivative of y of x minus the derivative of 2. And on the right-hand side, the derivative of 0 is 0, so they went ahead and solved that. So the derivative of 3x squared is 6x. Now this middle term, the derivative of y of x, well, what could that be? Well, that's going to be y prime, also known as dy dx. Really depends on who you are and what you're trying to do. But we can call it y prime, we can call it dy dx. The derivative of 2 is 0, and then the 0 comes down. So if we want to try to solve for y prime, we're going to get y prime equals negative 6x, which if you take a look at the last slide, that's the same answer that we got, which we would expect to have the same answer. This is an example of implicit differentiation. We didn't solve for y and then take the derivative. We took the derivative and then solved for y prime. So now at this point, you might be wondering, if we're getting the same answer, why would I change up my method? I feel pretty comfortable doing direct differentiation. Why would I move to implicit differentiation? And the answer is that you might find some problems very difficult to get y by itself. So if we took a look at some of the problems below, here we've got x squared y to the 5th minus 3xy plus 5 equals 0. Now that's going to be really hard to get a y by itself because we have two terms with y and it doesn't necessarily just factor out. Or we could even have like e to the y minus y equals 3x. Again, it's going to be extremely difficult to isolate y, but we could solve this problem implicitly. And that's why we're going to do implicit differentiation. So let's take a look at example 1. It says, given that f of x comma y equals x squared plus y squared minus 25 equals 0, then find y prime and the slope of the graph at x equals 3. So, okay, so what we're going to have to do is we could try to find y, or we can try to solve this problem implicitly. And that's what we're going to do here. We're going to try to solve this problem implicitly. So if I want to take the derivative of x squared plus y squared minus 25, I need to remember that in this particular problem, I'm going to assume that y is a function of x. So this is really y of x. But it's also going to have a numerical value because I know that if x equals 3, then y will have some fixed value. So what I'm going to do here is I'm going to take the derivative of this function. So, and it's going to be with respect to x. So if I take the derivative of x squared, I'm going to get 2x. Now if I want to take the derivative of y squared, we actually have to use the chain rule. Because remember, y is some function, and it's being squared. So I'm not really sure what this function is. It is y. So the chain rule says, okay, take the derivative using the power rule, and then multiply by the derivative of the inside. So I would really get 2y y prime. So this is 2y y prime. And then the derivative of negative 25 is 0, and the derivative of 0 is 0. So I'm getting this here, 2x plus 2y y prime equals 0. Now if I want to get y prime by itself, let's just move the 2x over. So subtract 2x from both sides. and I'll get 2y, y prime equals negative 2x. Now let's divide both sides by 2y. I get y prime equals negative 2x over 2y. My 2's can cancel, so I'm going to get negative x over y. And that would be my y prime. Now they're asking for us to find the slope of the graph at x equals 3. So in order to do that, I need to figure out what is my y value. So if we take a look up here, we can figure that out. If I plug in 3 for x, x squared is going to be 9 plus y squared minus 25. So I'm going to move that 25 over. So I get 9 plus y squared equals 25. So y squared is going to be 16, meaning y is plus or minus 4. And we'll take a look at why we were getting a double answer. We're getting plus or minus 4. But to find y prime, if x equals 3 and y prime is plus or minus 4, that means that y prime will be 3/4, or y prime could be negative 3/4. I've got two different possible answers for the slope of the graph at x equals 3. And why is that? Well, the reason being, x squared plus y squared minus 25 is the equation of a circle with a radius of 5. So this is what we're looking at here. We've got a circle and the radius is 5. So if I were to draw a coordinate plane here, and I'm going to say that x equals 3, then I have a y value up here, and I have a y value down here. What is that y value? Well, we already solved it. It's negative 4 or positive 4, depending on if we're going with the one in the first quadrant or the one in the fourth quadrant. And if I want to find the slope, it's going to be something like this and something like this. And we calculated these. This is going to be negative 3/4, and this one's going to be positive 3/4. But that's why we're getting two answers. We're looking at a circle here. So when x equals 3, we actually have two different y values. And that's something that we're going to run into every so often in these types of problems. In example 2, this is going to be very similar to example 1. You might right off the bat realize that x squared plus y squared minus 169 equals 0 is actually the equation of a circle with radius 13. So they say find y prime by implicit differentiation and find the slope of the graph when x equals 5. So at some point where x equals 5, we're going to get two different y values. We're going to get 5 something and 5 something. So we can find that out by plugging 5 in for x and then solving for y. But let's go ahead and set up our implicit differentiation. So I'm going to take the derivative of everything with respect to x, d dx. So the derivative of x squared is 2x. The derivative of y squared, remember, y is a function. So I've got to use the chain rule. So I'm going to get 2y, y prime. Essentially, whenever you take the derivative of something that's not that's not our independent variable, this is d dx. So this means the derivative with respect to x. So if I take the derivative of anything that's not x, I'm going to get a prime afterwards because of the chain rule. So if I had x, y's, and z's, and I'm taking the derivative with x, I'm going to get y primes and z primes. But I'm not getting x primes. And we'll go over that probably in a future slide. But just remember that when we're assuming that something is a function, we have to use the chain rule. It's not just the power rule. The derivative of 169 is 0, and the derivative of 0 is 0. So this is 2x plus 2y prime equals 0. So 2y prime will equal negative 2x. Divide by 2y. And we're going to get y prime equals negative x over y, which is actually the exact same answer that we were getting on example 1. And it has to do with the fact that this is going to be a circle. So let's go ahead and find our y values. If I plug in 5 for x, I'm going to get 25 plus y squared minus 169 equals 0. So this would be y squared equals 144. Now remember, when you take the square root, we're going to have a positive and negative root. We're going to get y equals plus or minus 12. So if I want to plug in these points, I'm going to get 5, 12, and 5, negative 12. And that means I'm going to get two different answers for y prime. Y prime will equal positive 5 over 12. And it could also equal negative 5 over 12, depending on which point we're looking at. So this would be our negative 5/12. This would be our positive 5/12 for the slopes. Example 3 says find the equations of the tangent line to the graph of y minus xy squared plus x squared plus 1 equals 0. So at least we're not dealing with a circle this time. So the first thing that we need to do is we need to take the derivative of both sides. Again, we're taking the derivative with respect to x. So if I take the derivative of y, I'm just going to get y prime. Now I need to take the derivative of xy squared. Now remember, xy squared, this is a product rule. So my first function will be x, meaning f prime is going to be 1. My second function is going to be y squared. So that derivative is going to be 2y prime. And with the product rule, we're going to cross multiply and add. So cross multiply and add. So that'll give us y squared plus 2xy prime. Moving on, the derivative of x squared is going to be 2x. The derivative of 1 is 0, and then the derivative of 0 is 0. So don't forget about this negative. We're going to have to distribute that. So we're going to get y prime minus y squared plus 2x, or not plus, it's going to be minus 2xy prime plus 2x equals 0. So we're trying to get y prime by itself. So let's move everything without a y prime over. So that means add a y squared and subtract a 2x. I'm going to get y prime minus 2xy prime will equal y squared minus 2x. The next thing I'm going to do is I'm going to factor out a y prime. So this becomes a 1, and the y prime just goes away here. So I'm going to get y prime times 1 minus 2xy equals y squared minus 2x. So I need to divide both sides by 1 minus 2xy, 1 minus 2xy. So on my left-hand side, these cancel. And on my right-hand side, I just have y squared minus 2x divided by 1 minus 2xy. So that would be my answer for y prime. Y prime equals y squared minus 2x divided by 1 minus 2xy. So I'm still going to have to plug in, but this is my y prime. So they say at the point or points where x equals 1. So if I want to find the value when x equals 1, I need to take x equals 1 and plug into my equation up here. So I want x to equal 1. So if I do that, I'm going to get y minus y squared plus 1 equals 0. So I'm going to start working on this left-hand side here. So that's negative y squared plus y plus 2 equals 0. Let's multiply everything by negative 1. So I get y squared minus 1 minus 2, or minus y minus 2 equals 0. So I want two things that multiply to be negative 1, or negative 2, but add to be negative 1. So this is going to be y minus 2, y plus 1, meaning y equals 2 or y equals negative 1. So I'm getting two values for y here, which means that I'm going to get two different answers for y prime. Remember, x equals 1, but y can be 2 or negative 1. So let's plug in x equals 1 and y equals 2. If I do that, I'm going to get y prime equals 4 minus 2 divided by 1 minus 2 times 1 times 2. And that'll be 2 over 1 minus 4, negative 3. So I get negative 2/3. And let's see what happens when I plug in 1 and negative 1. Negative 1 squared is 1 minus 2 divided by 1 minus 2 times 1 times negative 1. So this would be negative 1 in the numerator divided by positive 3, I believe. So getting negative 1/3. So those would be our two answers. 2 over negative 3, so negative 2/3 and negative 1/3. And example 4, we're going to be finding x prime, where x is a function of t, and they say that we're going to be doing implicit differentiation here. So they say t ln x equals x e to the t minus 1. So remember, this time we're going to be taking the derivative with respect to t. So we're taking d dt. X is no longer an independent variable. They also say evaluate x prime at t comma x, which will equal 0 comma 1. So this is really saying that t equals 0 and x equals 1. And that's going to make our life way easier at the end. So if I'm going to take this derivative, well, the first thing that's going to happen is this is a product rule. My first function is t, the derivative of t, so my f prime will be 1, because t is my independent variable. It's kind of like what x was in the last problem. And my second function is ln x. So the derivative would be 1 over x, cross multiply and add. I'm going to do t times 1 over x plus 1 times ln x. And that is going to give me a left-hand side of t over x plus ln x equals, well, now I'm going to have to do another product rule because this is a product. So my first function is x. The derivative of x is going to be x prime, because remember, in this case, it is the dependent variable, not the independent variable. My second function is e to the t, and the derivative of that would be e to the t. And now we're going to cross multiply and add. And when I do that, I'm going to get e to the t x prime plus x e to the t. So this is my derivative. And, oh, up here, I think I'm missing something. When I take the derivative of ln x, it should be 1 over x, x prime. So when I cross multiply, I get t times 1 over x, x prime. So this might look like it's really confusing, But I know that t equals 0 and x equals 1. So if I start plugging in, I'm going to get 0 over 1 x prime plus the ln of 1 equals e to the 0 x prime plus 1 e to the 0. So 0 over 1 is 0. So this whole term goes away. Ln of 1 is 0. E to the 0 is 1 x prime plus 1. So move the 1 over, I'm going to get x prime equals -1. And that'll be my final answer. It makes the problem a lot easier when they tell us what the values are going to be. So they just said once we take the derivative, plug in 0 for t, plug in 1 for x, and we get x prime equals -1. So closing thoughts, I know that implicit differentiation can seem really confusing, especially right when you're getting started. If you take a look at the homework, that should clear things up. The homework starts out very, very simple and progressively gets harder, but at a very nice pace. So I've found that in the past, people will see implicit differentiation and be like, holy cow, this is hard. And then they start taking a look at the homework, and it's really not too bad. And in the next section, when we do related rates, you're going to see some really cool applications of calculus that rely on us being able to take implicit differentiation. So if it's confusing, just take a look at the homework. Feel free to email, reach out, however you want to communicate, and I can hopefully help you. But I have a good feeling that once you start looking at the homework, this is going to get a lot easier. The big thing to remember is that the variables are not acting like they used to. If you have an independent variable that's normally x, then yes, we take the derivative just like normal, but our dependent variables that we're calling functions start getting the primes afterwards. So if it's a dependent variable, it gets a prime after you take the derivative, and that's from the chain rule.